Let's look at the solutions for these homeworks. The second part 8 of 8.1, so there are only 4 that I had assigned. And so in this problem, remember what we did in the lecture video. I showed you this algorithm that calculates the optimal number of attendees you can have given a certain schedule. And that's of course nice, but what you really want to have is the optimal schedule, right? Then that's, you're gonna want to schedule this. Now if you know what the best solution is, you want to use that solution, right? Okay, so that's what I'm gonna discuss now today. So let's remind us ourselves what the situation was. And here was the example, right? We had these 7 talks, and then we had defined this index pi. That was always an index less than the ith talk. Right, so this here is this pi. There was an index that is less than I, and it's the last one that is still compatible. Okay, and then we had calculators in this particular example what this is, and there's another homework that I'm not going to go over with, where you actually have to verify all this and do these calculations with it. And what we do then is we subdivided the problem in depending whether we had an optimal schedule or not. So we had 2 cases. We say if J belongs to an optimal schedule, then this is best of the most number of attendees if you only concern yourself with the first J many talks, right? If not, then you have to solve the problem for, you can delete this talk from your list and do it with a lesser list. Okay, and this was then the procedure that we used. So all the information that we need is here, because what is it, when is, from this it's also clear when is something an optimal talk. Well, if we are in this situation, right, that's exactly when we know that the talk is optimal. And how do we know this? Well, we can verify. So if our optimal talk is this one, now when is this happening? Of course, when this number here is bigger than this number, because we take the maximum. Okay, when we take the maximum, we are in this case exactly when we have this talk. Now, by the way, I should say it's not true that there is only one solution, right? There could be that there are, for instance, imagine this, 3 talks, all at different, non-overlaps. No, that's not what, yeah, 4 talks. Sorry, I want to point this out here before you make this mistake here, perhaps. Okay, let's say we have this talk, we have a talk here, we have a talk here, and we also have this talk. And here is 5, here is 5, here is 5, and there is 15. So, you have now 2 solutions, right? You could take this, let's make it green. This is an optimal solution. You will have 15 people talk, but you have 3 talks. But the other one is also an optimal solution, but it's a different one. So it's not true that there's one single optimal one, but we only want one of the optimal schedules, right? Then you can start arguing, okay, then I want to compare, but how many talks are we doing, because it's less shuffling around and so, but let's not talk about that now. Okay, so what we're gonna do is modify our procedure very quickly. So first of all, of course, we won't no longer call it max at, but let's say optimal attendees. Okay, it's a schedule now. So, and what we will do is we'll make, let's call S the schedule of so we're gonna so I'll do this, what I'm adding, I'll do this in purple. S0 is the empty set. So that, oh sorry, empty set. Let's write like that. So S at n, so we will return S of n. And this will be a list of talks that are optimal. So this will be the optimal list. That's the goal. Okay? And of course, when we start with nothing, our optimal list is empty. That's this initialization that do. Now, we have to calculate Tj, and Tj is the maximum of these 2 things, but we need to know when this is happening. So we should replace this by the query that if this guy, so if let's like it, I'm not going to do the bold-faced count. Well, okay, I'll do a little bit. Sorry, let me do this first. Okay, all right. Okay, I'll try to do a little bit. So if I'm going to replace this thing here by another clause. So if wj plus t times pj, if this number is bigger than tj minus 1, then this means j is part of the optimal schedule. So I'm going to add that. Okay, so then, well, two things. One thing is that the maximum will be that number, right? So I'm going to declare tj then actually to be that number. Okay, so let me, again, I'm going to repurpose this a little bit. So I'm going to erase this. Okay, so tj is this number, it's the maximum, right? And s of j is the previous best schedule, s of j, sorry, this should have been low, this should not be, this should be in thin, right? This is, so then tj is this thing, so this is now in the purple guy, yeah? And s of j is what we already found, and you add j to it. Sorry, no, it's what I'm saying is wrong, right? It says that your optimal schedule, if you remember back how we did this, was, remember our optimal schedule was part of this one, the optimal schedule inside this one, together with this one. So that's what I have to say. So I'm sorry, I made a mistake here. Then Sj is Sp of j together with j, and else, so okay, I'm going to get this now out of the way. Else, what happens else? Well, it's clear, right? Then we know what the maximum is. Then the maximum is given by the other guy. So else tj is tj minus 1, and sj is sj minus 1. In other words, what we had already done for, in other words, remember, this is the case where j is not part of the optimal schedule. This is this case here, right? And in that case, we could have just deleted j from our total list. Okay, so we reduce it to the previous solution. Whereas, I just want to stress this, in this case, you don't go back to the previous sj minus 1, because that might be a total different solution, give me a different work. I have to go to this guy here. Okay, sorry, I have to go to the solution I get by the first pj minus 1, right? I have to find the best solution among these guys together with j. Okay, and that's the only modification. And so then I said at the end, S of n is then the solution. Okay, that was question 53, and then 56, which is a little bit long. So let me go this over here. Sorry, that was some notice from before. So number 56, there you were asked to, we have these numbers A1, A2, A3, okay, and what we want to find is the maximum sum of consecutive, this is important, numbers in this list. Okay, so for instance, we could have minus 3, let me do the example here that I give, 2 minus 3, so this is if you want D, 2 minus 3, 4, 1 minus 2, 3 here. So let's look at what happens if we take consecutive sums. Of course, each element on its own is a consecutive sum, right? So these values are possible values, but you could also have taken these two together and you get a value -1, okay? We could take these 3 together and we got a value 3. We could take these 4 together and we get a value 4. But just to give other options. I could have taken these three together, this would give me 0. Or I could take these 4 together, and that would be 7, 8, 6. Or I could have just taken these two. Let's do another one. I don't take different colors so that they don't overlap too much. I could have taken these two together and it gives me 5. You see, it looks like perhaps an easy problem, but once you're trying to do this, even with a list of 6 numbers, there's quite a lot of possible combinations. So it's not obvious at all which solution you're going to have to take. Now, of course, if all the numbers are positive, then it's simple, right? Take all of them, right? But the problem is that there are negative numbers that bring the total down, okay? And so, what does it say is, well, we're going to define mk, but be very careful. And this is, you might, okay, let me say it. mk is the maximal sum of consecutive numbers ending with AK. So in other words, AK has to be part of it, it has to be the last element, okay? So what this would mean, for instance, if I would do very simple, let's do A3, okay? What is A3 here? Well, it has to contain 4, and therefore there are not that many possibilities now, right? So I can do these two together, and that would be 1, or I could do these three together, and that would be 3, okay? Sorry, A3, I don't know where I said, I meant M3. So you see here that M3 is going to be 3, okay? Because I have to include AK, right? So in other words, what is this? We can actually write this up. What is this, right? This is the maximum of the summation. Well, from what is the sum here? Well, we go from some index I, from some index j to k, where j is less than or equal to k. So j is the start, so this is perhaps better to write it this way, aj plus 1 plus dot dot plus ak. And now we take the maximum of all possibilities where j can go from 1 all the way up to k. Okay, in which case we just have ak. Okay, so that's what mk calculates. And so then they say the following recursion relation holds. Mk is equal to the max of mk minus 1 plus ak, or ak. Okay, so well, let's think about it. Okay, if I have to end in ak, right? If I have to have a sum like this, what are the sums that appear here? These are all the sums that end in ak minus 1. So every sum that I want to consider in my calculation of mk can be split into, let me put it in, make it green here, these guys. So that's, what is the one before here? So perhaps the previous one is ak minus 1, right? So all these plus ak, right? This is how, so the green ones are the ones that are sitting in mk minus 1. Or, sorry, not sitting there, but I mean, we used to calculate, right? We have to take a maximum. We take the maximum of all those, okay? The green ones, because they end in ak minus 1, okay? And so, now, what is mk? Well, there are two possibilities in which for mk. Either the solution consists of just ak itself, in which case there is nothing in before that, or there are more elements involved, so it is something of this form, and therefore if we take away ak, we are something in that we use to calculate k minus 1. And of course the one that is the biggest here, and I add ak to it, is going to make it bigger. Well, is it? That we don't know, right? Because it could very well be that that this is negative, right? Or it could be that this is negative, and that's actually what can happen. If this is negative, and I add ak to it, then this will actually be smaller than that. Okay? So this helps us find out, be careful, mk could be negative, right? So here m3 was 3, but let's look at what m2 was. In m2, well, it's the maximum, there are only two, the max of what? It has to end with a2, so it could be a1 plus a2 or just a2, right? So a1 plus a2 is negative 1, and a2 is negative 3. So the solution here is negative 1. It's a negative 1, unfortunately, but it is better than taking just a2, right? And so now if we want to calculate what is the best solution for 3, well, so let's now see here, what we just said, is this true? That is the maximum of m2 plus a3, so a3 was 4, right? Or 4. So right. Oh, I said m3 was 4. That was a mistake, right? Because m3 is 4. Yeah, now I see that I made a mistake. I forgot the best solution, namely just 4 itself. Silly me. I was trying to take the one that I was thinking of taking all 3 together, then I get 3. But that's not the best solution. You see, if you do things recursively, you actually sometimes find your own mistakes, right? So now it's clear, right? Because m2, we already calculated m2 is negative 1. So this number is, which is 3, is less than 4. So m3 is even 4, okay? So that's what we have. And once we have established this, we can now do the programming, right? So what you have to do then? Well, you calculate. So what is now the answer going to be? Let's make it this way, right? So we at the end, I'm going to leave writing the algorithm calculator mk to you. That's kind of, I hope you can do this, or perhaps I'll do it in the end. But let's think out what is the solution. We're going to have m1, we're going to have m2, all the way up to mn. So n is the number of elements in the list, right? Now, we're looking for the highest number of consecutives. Now, that ends with some element. Let's say it ends with 7, right? The optimal solution ends with a 7. So which of these numbers is going to be the biggest? M7, right? Right? Because if that's the best solution, it's going to be this number, because M7 is all the solutions that ends in A7. And I'm saying the best solution ends in A7. So that's going to be M7. So in other words, what we'll find is at the end that M is going to be the maximum of these numbers. So that's actually the solution, not MN. At the end, MN could be actually very bad, because the last number could be a very, like for instance here, minus 100. It's clear that MN is never going to be, you can never have something that ends in minus 100. That's going to really screw up your maximum, right? So it's the maximum is attained at M. Now for the programming, so okay, perhaps I should do it though. So we have to calculate MK, okay? So how do you, what do you do for that? Well, it's recursive, right? So the calculation of M, let's call it the algorithm M. So what you do is, there are two cases, right? What you do is, so I'm going to do the main part, right? The blah, blah, blah procedure, this and plus after that, and initialization. And so, okay, initialization, perhaps M0, and M0 is 0, okay? So there's a couple of stuff, but let me not do everything, okay? And so I'm going for I going from 1 to n. Sorry, I should put this here. Okay, sorry, let me do it here. So I'm not sorry about this, but it takes way too long if I have to write this here with boldface, not boldface. I could perhaps do it this way. Okay, these are the... okay, so for 1 to n, so I said I'm going to do this and I forgot to do this. M0 is 0, okay? And so we're going to define mk. So for k going from 1 to n then, okay? If mk plus ak is bigger than, sorry, no, ak minus 1. Because that would not make sense what I was saying, because I'm calculating mk. If mk plus ak is bigger than ak, then mk is going to be that new number. Else, mk is ak. Right? That is just saying calculate this a maximum. That is a way of calculating the maximum. You look at the first element, is that the biggest, then that's the maximum, and otherwise it's the other one. Okay? Oh, sorry, this is supposed to be in this. Okay, so now this loop calculates mk, and then the final thing is return the maximum of m1 up to mk. Of course, you could also do this. It's kind of a bit cheating, because actually that is also a little bit of an algorithm, right? So we should then say the optimal. Yeah, I'm not going to discuss that, but this is really what the main dynamic programming is. Okay, and so again, why is this overlapping problems? What can happen here? Well, these two cases that we have. This case tells me, okay, you have to look at the previous solution of the previous numbers and add ak to it. And this says, forget about the previous ones, just start with ak. Okay? That is two different solutions. They overlap, right? In fact, they both have ak in common. By definition, because it has to end in ak. Okay? So this is how we divide this problem into... now again, this particular algorithm that I wrote down is calculating for me what's the optimal value. What I should of course calculate is, well, what is the optimal, that's a bit more complicated. I don't want to do this. I don't know whether this was even part of the question. You could ask, okay, give me now the optimal solution. Tell me from which index to which index. Okay. Of course, I will know that whenever the maximum, remember, if the maximum is 7, I know it ends in 7, but I still don't know exactly where it starts. Now, of course, what you could do is work down, right? Look at all the possibilities for M7 and look at which one is the highest, and that will give you. Okay. And then it was asking you to do this on this particular problem, but it's a little bit of too much writing. I'm not going to do this in the solution. Okay.